Hey, everybody. So we derived the formula for the range formula, and that allows us to find the displacement in the x direction when an object is fired off over level ground, meaning delta y is equal to 0. So I thought we could plug in a few problems, see how it's useful, and what we can kind of gain from that formula. So let's take a look. How about if I fire this thing off at 12 meters per second at 45 degrees? Let's take a look. Oh, is it going to hit the target? Yes! Now, the objective is not to hit the target. The objective is to understand physics. But it does feel good. So, we just had an initial velocity of 12 meters per second. We have an angle of 45 degrees. Let's go to the math and see how this works. So, here's the range formula as we derived it just a moment ago. Let's go ahead and try to plug in some numbers. So our formula of dx is the velocity squared times the sine of twice the angle, all divided by g. So in the problem that I just did on the PhET simulation, I always go and draw a simple picture. So it was 12 meters per second at 45 degrees. And I always draw in the path of the ball or pumpkin or whatever we're firing off. And what I'm trying to solve for is dx. It took me 12 additional seconds to draw that picture, but it's key going forward to sort of see what we're solving for. So let's plug in some numbers. So dx equals v squared times the sine of twice the angle, all divided by 9.8. Get your calculators out. Let's plug it in. So I'm going to have 12 squared times the sine of 2 times 45 degrees. Yeah, I know. Divided by 9.8. Now, 2 times 45 is 90. What's the sine of 90? It's okay if you don't know. It's all right, because you know what does? Your calculator. But I won't tell your geometry teacher. Honest. So 12 squared times the sine of 90, which is 1, all divided by 9.8, I got approximately 14.7 meters. See how easy that is? That's awesome. Let's go ahead and go back to the simulation. If I use this range finder and I put it right where it hit, what do I get? Plus or minus there, I get 14.68 meters. Gosh, that's close. Nice job, PhET. Good. Yeah, that was pretty easy. All right, we're back. So here's what I'd like to try. What if we want to hit a target that is 15 meters away, but the object is traveling at 18 meters per second? What angle should I set the cannon at? All right, let's go. Next thing I do is I draw a picture. I'd like you to time me. Right now, while you're sitting at your kitchen table or the desk in your room, I want you to count 3, 4, 5, 6, 7, 8, 9, 10. Well, that's getting annoying, isn't it? That took me 20 seconds, maybe 30. I'd like to find theta. So our formula dx equals v squared sine of 2 theta over g. Let's get theta all alone, and that's a bit of a process. I'm going to first multiply both sides by g. I'm then going to divide by v squared. And I think right now, I'm going to pause and plug in my numbers. Okay, so if I have a range of 15, gravity on Earth is 9.8 divided by 18 quantity squared. That will be equal to the sine of 2 theta. I need you to get your calculators out and punch it in. If I'm smart enough on the Ed puzzle, I'm going to stop it and make you guys get this right. I got 0.454 approximately. I'll keep my answer in my calculator. Equals the sine of 2 theta. Now, that 2 theta is wrapped up in the sine. So in order to get it out, I need to take the inverse sine of both sides. So when I do that, I get the sine. I'm sorry. When I do that, I have to take the inverse sine of 0.454 is equal to, when I take the inverse sine of the sine of 2 theta, I end up with 2 theta. Okay? Inverse sine, answer, second function answer. I'm going to round to 27 degrees equals 2 theta. And it's only now that I can divide by 2. Oh, this is embarrassing that I've reached for my calculator. Of course, that theta would be 13.5 degrees. Let's go to the sim. So, if I come over here, I can set that angle at 13.5 degrees. Let me see if I can click on it and type it in. That is unfortunate. I can't find the angle at 13.5 degrees. What do I do? I could edit the video, change everything, but no, I'm committed. I've got another idea. Let me ask you a question. By the way, 13.5 is totally the right answer for the question as we laid out, but it's only one of the answers. Ready? All right. Here we go. Put on your thinking caps. Say we were to fire off the projectile at 30 degrees. It's going to go. That would be at my angle of 30. Now, just humor me. What is the sine of 2 times 30 degrees? So it would be the sine of a 60-degree angle, which is root 3 over 2. But for my calculations today, I'm just going to let it be 0.867. All right? What if, instead of 30 degrees, I fired off at 60 degrees? Like that. Well, let's see. If I take the sine of 2 times 60 degrees, what do you get? Punch it into your calculator. You know what you get? Yeah, no kidding. You get 0.867. So if they each have the same velocity, a 30-degree angle and a 60-degree angle give us the same range. Now, in case you don't see the connection there, let's try an angle of 13.5 degrees. What is that? I'm going to ask my calculator. What's the sine of 2 times 13.5? It says 0.5454. Hey, that sounds familiar. I want you to also plug in 76.5. So what is the sine of twice 76.5 equal to? That's right. No, wait, you didn't punch it in, did you? It's 0.454. What can you tell me about 30 and 60? What can you tell me about 30 and 60 and 13.5 and 76.5? Yes, that is right. You guys are not only good-looking students who are smart with a bright future ahead of you, with a great fashion sense and fantastic athletes, you also know that it's a complementary angle. That's why I was just complimenting you, right? Now, complementary angles have the same range. So if we were to go back to our simulation, and since 13.5 didn't work, I should try 76.5 and see if that will do it for me. Now, this doesn't allow me to adjust it as precisely as the old setup, but I think I can get to 75 degrees at my velocity in this case was 18 meters per second. Let's fire that baby off. This is in slow motion, by the way. And the range that we were shooting for. Let's see. This says 16.51. Why is it slightly off? Because the angle is slightly different. But I think we can utilize this simulation to get to see what's going on with complementary angles. If I fire this off at 60, I'm going to go normal speed here. Oh, hit me right in the head. Let's try that at 30 degrees. Oh, gosh, that's beautiful. If I try 35 degrees, and the complement of that is 55 degrees. Bam! Same exact place. What if I try 45? Yeah, that's right. What's the complement of 45? Yeah, it's 45, isn't it? What's the sine of 90? Because if I look at the range formula, v squared sine of 2 theta, so for 45 degrees, let me finish this thought and then let's call it. For 45 degrees, if I plug that into dx equals v squared sine of twice the angle divided by g, if I go ahead and plug in 45 degrees here, this becomes v squared times 1 over g, which is going to be the greatest value that I can have. Well, so what does that mean? That means that if I fire off something at 45 degrees, in the absence of air resistance, that's the farthest an object can go. All right, I feel myself petering out here.